from Heidelberg University for a talk on Dirichlet-Neumann averaging and how could be Gaussian process simulation efficient.
Okay, thanks. So now that both of the organizers aren't here, I'm still gonna say what I wanted to say. It's great that the small countries, Uruguay and Austria, presenting, which make up, I just looked it up, about 0.1% of the world population, setting 6 of the speakers, 20% of the speakers. So we're punching way above our weight. And I'm gonna talk today about something completely different to the previous talk. But as I'll show on the next slide, it provides an ingredient that is crucial for the Bayesian inference that we just saw, and also for other talks that we'll see later today and tomorrow. So in particular, I'm interested in how to efficiently simulate Gaussian processes, which might be used in uncertainty quantification or in inference. This is joint work with my PhD student, Robert Coutry, who I should credit for doing most of the work on this job. So here are just 2 motivations for it, which basically just set the scene because we haven't really seen many talks on this yet. It was mainly math finance and other topics. But if we want to do uncertainty quantification, if we have some physical problem like a PDE, like a diffusion PDE, simulating subsurface flow, you might be interested in studying the uncertainty with respect to variations in the parameter when you want to calculate some statistics of the output. Or, and this is related to the previous talk, if you want to actually estimate parameters in a model, or if you want to predict certain things with your physical model under or given some data, so you have some sorry, I should have put a different G here. So we are measuring some G, and then we want to calculate some statistics on some H of some pressure field, for example, as it is in this diffusion problem, under the posterior. So given the data, we might want to calculate this. So in a Bayesian setting, what one would do is one would put a prior distribution on this parameter U, and this would be, for example, again, a Gaussian. So in both cases, I need lots of Gaussians, and I need them typically on a fine mesh resolution. So here I have a sample of a non-stationary Gaussian random field, which you might use to model subsurface properties or other material properties, or in environmental simulations that we just saw. You typically want to do this in R2 or R3. So you need, if you have a higher resolution, you'll also have in the order of millions to billions of grid cells here. And you want to simulate on a fine enough grid in order to pick up fluctuations in this random field. And so both on the definition of what a Gaussian random field is, and in practice, one looks essentially at a vector. Take a subset of points in your domain, then a Gaussian random field is defined as the field, or basically that the vector of values evaluated at any subset of points of the domain is Gaussian distributed with a certain mean, here for simplicity always 0, and covariance matrix, which is a huge Rn cross n matrix if the number of points are large. And so in practice, we need this on a very fine grid. And so the question is, how do we efficiently simulate this? So this is obviously a very old topic, but it's still not, at least I will try to convince you today, it's still not fully solved. So how do we, or what are ways to generate these random fields? So the general idea, and we're not diverging from that, is that you will factorize your covariance matrix. So after discretizing, you'll have an n by n in general complex, or you factorize into n by n block H and H Hermitian. And then if you've got this factorization, you can take your favorite method to produce independent Gaussians and then just multiply with the factor H. And that gives you correlated samples at a large number n of points. So what would be classical ways to factorize? One would be simply doing a Cholesky factorization. It's a covariance matrix, so it's symmetric positive semi-definite. So this is always possible. But you could also analytically set up your already factorize your differential operator, your covariance operator. This would be the Cohen and Löw expansion in for example, in the Matern case, or you could take Fourier type methods. But in order to use Fourier type methods, we need periodicity, so we need to embed in a larger matrix, and that's called circulant embedding. What are the problems? What are the challenges? If you go via Cholesky factorization, which is essentially the go-to method when you've got small n, the problem is it scales rather bad. If you've got a dense covariance matrix, it could be as bad as n cubed. But in general, you will have something like n to the 1.5 in if you take a sparse direct solver. You can use approximate Cholesky. You can pivot and truncate after a certain number of steps, which has been analyzed in this paper by Habrecht et al. But then you need to worry about what rank to choose and how high rank you get, and that might lead you to the same problem as in the second case. And the second case is that you, in the Cohen and Löw expansion, if you have a rather smooth random field, you might need quite a lot of these vectors to store in your matrix, in your eigenfunctions or eigenvectors, and this could be costly and then also costly to evaluate. Finally, the circle embedding, which is sort of from an n order n point of view, the best scaling one, because it's n log n, in the sense that you just use fast Fourier transform to do it. But the problem there is if you have smooth random fields, smooth covariance functions, or long correlation lengths, or you want to sample on a very fine mesh, then you actually need to embed. You need to pad your matrix, because just simply doubling it and periodizing, which is the plain vanilla circulant embedding, will not guarantee that the matrix is symmetric positive definite. And you would have to either approximate or you, by setting the negative eigenvalues to 0, or you need to embed in a larger domain. The advantage, though, is apart from the n log n, is that it's exact. It provides you, if you can do it, it provides you with the exact covariance structure between the points. Yeah. Okay. Hierarchical matrices. Sorry, I sort of talked about that, but you could do hierarchical matrices, which would also be a way of doing it. Yeah. That's sorry. I'll put that on my next time. So we will start and mostly for today talk about isotropic random fields, but I will come to non-stationary random fields later as well. But in an isotropic random field, you assume that the covariance is only dependent on the distance between 2 points. And you have a certain covariance function rho that encodes this. This function rho, I will come to in a minute, will have some smoothness properties. There's also a length scale parameter L, which scales how at what distance these points correlate. And basically, it means that the covariance matrix or operator is essentially given at 2 points x and y as this distance, as this function of this distance. One classical family, and which is used heavily as priors in these Bayesian inference problems that I mentioned, or in UQ problems, is the Matern family of covariances. So the covariance function rho there is simply this function that you see here. It's a function of the distance. Depending on this new parameter, you either have a very fast decay and a very light tail, or you have a slower decay and a heavier tail. That's one of the things that the new parameter influences. And the other thing it influences is what happens at the origin. So at 2 points that are very close to each other. And this controls the regularity of the field that comes out. The larger nu, the more derivatives of your function you can take, or the more Hölder derivatives. An important parameter derived from nu and lambda, from the smoothness parameter and the correlation length scale, is also kappa, the reciprocal correlation, because there's also a link to so-called stochastic PDE, the stochastic PDE, the SPDE approach for sampling random fields. And the person who developed it is actually here in KAUST. And I met him the last time I was here. So Harvard Ruhe and co-workers have basically taken some old relationship between the precision operator given here and the covariance operators that the Matern family defines, and have shown, well, they haven't shown, they just exploited that for the right choice of kappa and beta, you can essentially simulate a Matern family covariance field by essentially putting white noise on the right-hand side of this differential problem, fractional differential operator. This beta could be a fractional power, and it essentially allows you to sample from a random field, a Matern random field, by solving this PDE. So you're essentially sticking in something rough, and you're applying some differential operator or the inverse of it, which basically means I'm smoothing it, and therefore I get more correlation. And the main observation in this paper here is that you can do that efficiently with finite elements, for example. You can solve this PDE with classical techniques for solving PDEs, and therefore you can then go to arbitrary domains. You can use non-uniform grids. You don't need structured grids as you would need for Fourier type methods. And most importantly, you can also very easily come up with nice models of non-stationary random fields. So you can both make the correlation length scale, kappa, or the parameter that related to the inverse correlation length scale, non-stationary or x-dependent, or even the diffusion coefficient. And this is also another nice advantage of this SPDE approach. But as you can see, this is posed on all of our D in principle. And if I restrict it to D, to a bounded domain, I need to set some boundary conditions. Otherwise, this is not a well-posed problem. And then the question is, and this is what the starting point of my student's PhD was, what happens with the dependence on the boundary conditions? You will lose the isotropy of your field, and you will incur errors in the covariance. So here is a new way of sampling, which is sort of in the spirit of we first periodize and then discretize, rather than discretize and then periodize, which is what FFT, like circle and embedding, would do. And you essentially just exploit some classical links for between Fourier space and real space in the so-called Poisson summation formula. So the Poisson summation formula on a lattice, so these are ZD, essentially says that if I sum over the function at these lattice points, it's the same as if I sum over the Fourier transforms of the function over the lattice, provided you have these weak conditions here. And so you can always periodize a function by essentially using this Poisson formation formula, and you end up getting, so depending, we do two things. We periodize, but we do it with a scaling. So we introduce a scaling parameter here. So obviously I can introduce a scaling parameter here, and the same thing holds still true. And I'm introducing that scaling parameter in such a way so that I essentially periodize. I can choose with alpha on what box I'm essentially periodizing, whether I periodize on -12, on 1, 1, 2, 2, etc. So here we have, for example, a periodization on -0.6 to 0.6, or -0.9, 0.9. You see in red the true covariance, and in blue the approximate, and you see here that if I'm only interested in this covariance function from -1/2 to 1/2, say, then it's only very small error near the boundary that I'm incurring. So let's, as I said, stick with isotropic covariances. And certainly for the first part of my talk, which is Fourier-based, I'm going to only stick to these isotropic covariances. So our goal is now to essentially construct our random fields based on this approximate periodized covariance function. So instead of phi, I use this periodized one with some parameter alpha in it. And I'm going to construct a random field that has the same mean as our original field, for simplicity 0. And the covariance structure now is essentially not phi anymore, but phi alpha periodized. And the nice thing in comparison to circle embedding is that by Bochner's theorem, we automatically get that this is positive definite. So we don't need any embedding. We have a periodic function, so we can use FFT, no worries. Contrary to the circle embedding case, the way you can think of it pictorially is we change the function even inside the domain we're interested in. So this is the blue one here, whereas the circle embedding, it basically just takes the Fourier transform of phi times the characteristic function cut off at -1, 1. So it is correct. It's exact all the way up to here. But where we periodize it, it has a kink. And that kink is basically what ruins your positive definiteness, or can ruin your positive definiteness. And that's why you need to potentially go further than -1, 1. So now we can use, with our approximate covariance function, phi alpha periodic, we can use a Fourier transform, which is efficient, which is n log n. And we can now define our solution to our random field as simply the field given here, which is simply the expansion on the lattice of with the Fourier coefficients coming from this periodized from the scale function. Yep. Yes. I'll come back to that. I'll come back to that at the very end. Yeah. At the moment, rectangular mesh is crucial. Yeah. Sure. So what does periodizing do? So I mean, to the naked eye, it's a little bit hard to see, but if you have a periodized one, this would be an example of a periodized one in 1D with the covariance matrix here. This would be a non-period, correct one, which is isotropic across the whole domain. So interiorly, they look similar, but obviously trajectories have to match when they come to the ends. So what people typically do is they simply throw away half of it. This is what FFT, what circular embedding would do. Throw half of the field away. Then on the half of the domain, you don't have the periodic effect, and then you rescale it, and you have your field on your original domain that you're interested in, or you simulate on a twice as large domain. Now, this is the second idea. So the first idea is periodized and discretized. The second idea, and this is the crucial idea, is once we started working on this, or once Robert started working on this, he realized that if I put, because most people in the SPDE world would put Neumann boundary conditions on the boundary, but when he actually experimented with Neumann and Dirichlet boundary conditions, he observed the following phenomenon. So what we're after is in 1D is this covariance. What you get with Dirichlet, with Neumann, with Neumann you get this one. So it's 2 at the end, 1 in the middle. It should be 1 along the whole diagonal. And if you do Dirichlet, you get 0 on the boundary and 1 in the middle. And if you do periodize on this domain, you get this very poor random field. But if you now look back at these two and just look at the diagonal, along the diagonal, you see that they're literally opposite to each other. The error they make is opposite to each other. And this is not an accident. This is actually what we exploit next. because you can actually explicitly work out the covariance function. This is just 1D for the beginning. You can work out the covariance of these fields with Dirichlet and Neumann boundary conditions. And you see that the sort of the perturbing term appears to be exactly the same with different sign. You subtract, so you first of all, you get your phi on a twice as large 2 alpha box periodized, minus this term that we don't want, doesn't depend on the distance. And here you get it with plus. So this is why we call it Dirichlet-Neumann averaging or DNA sampling, because essentially you take 2 samples, one with Dirichlet, one with Neumann conditions, you sum them up, you scale them correctly, and you end up, and you can prove very easily that you end up with a field that has exactly this periodized covariance structure and, in fact, on a twice as large domain. So without embedding in twice as large domain as you would do in circular embedding, we work on the regional domain, not on a twice as large one. We get a field that's periodized on the 2 alpha domain, but of course it's still not phi. Yeah? It's got the error in it, but it's correct.
So the omega is
No, this is very crucial. We really do 2 samples. Independent. Crucial. So later on, or maybe I can say it right now. So the circular embedding, if it works without padding, you just take a twice as long vector, you do 1 big Fourier transform, full Fourier transform. We do 2, we do a sine and a cosine transform independently, and then average the 2. The full one would also throw half of the field away, right? Well, it would use both parts, and it can use its real and imaginary part. So in the end, to cut to the to my final point, the cost will be roughly the same. Okay, so if you can do it in 1D, then you can do it on a box in 2D. You simply need to average 2 to the D functions. We need any combination of Dirichlet and Neumann. So in 2D, it would be Dirichlet in X, Dirichlet in Y, Dirichlet in X, Neumann in Y, and so on, all 4. And now I need to scale with 1 to the D on 2. So I need to scale with a half in 2D. And I can prove again that this field has the 2 alpha periodized covariance structure. And now I can also truncate this to a finite domain. So I can discretize and only use a finite lattice. I don't want to use ZD. I want to use a finite lattice and use only n terms. And then the same holds. So it's the discretized and periodized covariance function appears on the right. Here's a picture in 2D. So this would be the sum of the 4 fields independently created. It is 1 everywhere. You don't see any artifacts. And here is the 4 constituent fields in the corner. So you see this would be the Dirichlet one, Dirichlet one. This would be the Dirichlet-Neumann one, Neumann-Dirichlet, and Neumann-Neumann one. If you add them up and scale them by a half, you get exactly an isotropic random field with the 2 alpha periodized covariance. Now, I have made an error, and I said that I'm not taking, as in circular embedding, the exact covariance structure, but we can prove rigorously what the error is, and the error is exponentially decreasing in alpha. So if I choose alpha, my embedding large enough, so we will typically just work on the original domain -1, 1 or 0, 1, depending on which one we define it on our domain D. But if you want to make the error small as you wish, you only need to make this domain, you need to grow this logarithmically. So the error goes down exponentially for any new greater equal to 1/2 and alpha greater equal to 1. And there is some condition on the alpha, an extra condition, but for all the fields that we're interested in, you can essentially choose alpha equals 1. No, the cost does grow. The alpha, if I increase alpha, it's the same as padding for circular embedding. No, I'm solving on a domain minus alpha to alpha. I'm just saying in practice, we will choose alpha to be 1 all the time. I can also include the discretization error. So I can include what error we incur with your Fourier transform, or with a discrete Fourier transform truncated to a finite lattice. And that depends on the smoothness of the field, how fast that decays with n to the minus 2 nu. So here is what it does in practice. So in practice, we're comparing problem size, so degrees of freedom, how fine we sample the field. So we've got mesh sizes 1/8. So this is 8 by 8, 16 by 16, up to 2000 by 2000 grid. We're just averaging 5,000 realizations here. And we're comparing the runtime of both the original circular embedding and our DNA approach and the memory consumption. Now, I start maybe with the purple circles here. The purple circles is where circular embedding fails. So up above this point, so for Gaussian covariance, from this point onwards, I need more padding that we allowed ourselves, and we allowed ourselves 1,000 points in each coordinate direction padding. So even though we're only on a 16 by 16 grid, I need 1,000 points padding in order to make the Gaussian work. For nu equals 6, you end up here. For nu equals 2, you end up here. And I think for nu equals a half, you end up somewhere here. So if the orange curve is actually approximate circular embedding, where you set the eigenvalues that are negative to 0. So then this is sort of showing circular embedding in its best light. And we are essentially, apart from a startup phase, where our sort of bookkeeping or maybe our code is not optimized, and for small problems, we have some overheads, but then essentially it performs roughly the same. But it needs 4 times less memory. So that's one thing. Secondly, this approximate circular embedding produces random fields that have artifacts. So by throwing away negative eigenvalues, I actually create streaky type random fields. So you might not want that. So this is what ours creates. Okay, so the first part, and I'm a bit lost on my time. Okay. The first part of my talk is essentially how do I efficiently construct random fields by first periodizing and then using Dirichlet-Neumann averaging, Dirichlet conditions, Neumann averaging 2 independent samples or 4 in 2D to create genuinely isotropic random fields without artifacts. And the modification does create a small error, which we can prove is exponentially small for Matern, for example. It does not require padding in practice. There's no constraints on what H and alpha need to be. It doesn't create artifacts. And there is certainly memory efficiency due to the simpler DCT and DSTs. And it's also, at least these 8 or 4 fields can be done fully in parallel. So it helps a bit with parallelization as well. So that's the first part. But I also mentioned the SPDE approach. And the nice thing is that this whole theory and this whole observation completely carries over to the SPDE approach. So now we are solving a PDE on a domain D. And so the way that people in SPDE sampling, Ruhe et al., and then so in this first paper, and then later in this paper by Kristenko et al., it was analyzed more carefully from a numerical analysis point of view. People overcome the problem of this artificial boundary condition by also embedding in a larger domain. Arguably much less than for the circular embedding. We don't need thousands grid cells. Typically, the enlargement is by 2 correlation lengths or something on both sides. But you do need to increase the size of the domain on which you solve, and you have a boundary condition which will not affect your interior domain D quite as much, but it will affect it. The error will not be 0, and it will be quite significant. It will not be isotropic near the boundaries. And if you do need, especially for smooth fields, if you do need a lot of oversampling, then it can be actually expensive as well. And then finally, and this is really what drove us, it's actually quite difficult to implement, especially if you're in a parallel environment. Think about you have your problem on 256 processes, your PDE problem, and now you want to sample a random field. And suddenly somebody says, no, 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 you need to solve the random field on a larger domain. Then you need to come up with new processes that work on those bits of the domain. We don't. We just work on the original domain. We solve multiple PDEs on the original domains. And this is basically the corollary to the other result. If you take the same averaging of so if we periodize the random field, and if we basically, so this B stands for Neumann and Dirichlet here. So if we take again the same averaging of Dirichlet, Neumann, Dirichlet, and so on in 2D, I get a random field that is has exactly phi to alpha periodized as its covariance function. So the boundary condition effect is completely gone for any nu greater equal to a half, for any correlation length greater 0 in any dimension, with the mild condition again, which is for all the relevant correlation lengths that people care about, always satisfied. And you can use the same error bound. So the error again decreases exponentially with alpha. So again, we're gonna, in our practical computations, we're gonna choose alpha equals 1. So we work on the original domain. What implications does it have? First of all, you can essentially, by periodizing, you can express these covariances of SPDEs of solutions with boundary conditions given. You can efficiently, in parallel, construct them after you've done some finite element discretization, for example. You don't have boundary artifacts, and no oversampling is necessary in practice. However, it's for the moment restricted to cubic domains. I'll comment on that later. So here is the comparison for SPDEs. So this is quite a heavy graph, but essentially each line just corresponds to different correlation lengths. So we start with shorter correlation length, 0.05. This is correlation length 0.1, and this is correlation length 0.2 on the bottom. Sorry, can't get there. We again on the x-axis we have mesh size. So we ran 1 on 16, so 16 by 16 grid up to 256 by 256 grid. And for the SPDE, we use oversampling of 2 correlation lengths. So that means we oversample by 0.1 on each side for the first row, and by, for example, 0.4 for the last row. And the Matern is nu equals 1. That means we only have to apply the PDE operator once. Okay, what do we see? So if we start on the right is simply bang for buck. It's just time. How much does it take you to do it? And you see the longer the correlation length on the sort of more interesting, larger meshes, you clearly have a benefit from doing the DNA. For the intermediate or shorter correlation length scales, at some point, the oversampling is not necessary or is not very heavy, so it doesn't cost you much. In memory, you get, again, your factor 4 gain here for these shorter correlation lengths. And in accuracy, you essentially see no, you basically see no difference. Maybe the purple line I didn't talk about, you cannot do DNA, you cannot do SPDE without oversampling. So this is what you would get for without oversampling. You simply have no convergence with mesh size. Another thing just to add to this plot is the green line, just saying if you're on a, just to advocate, if you're on a uniform block with a uniform grid, then use FFT-based methods. Even if you're solving the PDE, thinking of solving the PDE method, just think of solving it in a Fourier basis. It's much faster and much more efficient. Okay, now to Alex's question. So yes, we can extend to more general domains, but so for example, if you take a circle, you can just sum up Dirichlet and Neumann. You get perfectly the field out. But if the corners are not 90-degree So at least the plain vanilla thing we're doing does not work. So you do see here, so this is where we averaged 4 functions, and we end up getting some errors here. This is where we simply put Dirichlet everywhere or Neumann everywhere, and then we get quite heavy errors here, but less error here, where there's essentially a very small corner or not very strong corner. But what I advocate, and I've already done this before, already since a long time, I advocate to anyway put it into a bounding box and then use a uniform grid to sample and interpolate. So in this paper, we've analyzed this. This is a lot more efficient than doing it directly on the original grid. I also said that you can do non-stationary. For non-stationary, so we're taking now a sort of a deep Gaussian process where we make the correlation length or the log of the correlation length itself a Gaussian random field, a stationary one. So the correlation length we make stationary, but we feed it into the SPDE that makes a non-stationary Gaussian random field for the actual random field. Here is so the effective coefficient is chosen such that it's roughly nu equals 1 and L equals 0.1. And we also make it a bit anisotropic by changing the diffusion coefficient. So now we don't have a reference anymore. We don't know what the true covariance should be because it's non-stationary, but you can clearly see that SPDE, so here on the right, so maybe I should start from the left. So the coefficient, the log of the coefficient is our draw from our U0. This is our correlation length parameter. This is a sample drawn from our DNA approach with SPDE. This is one drawn with the original SPDE approach with Neumann boundary conditions. So you see that they're not the same, even though they're solved with the same white noise right-hand side. And you see also in the covariance, in the marginal covariance, the pointwise marginal covariance, that there is definitely artifacts in the SPDE approach at the corners, quite strong ones. So the Dirichlet-Neumann average can be also used to get rid of the artifacts in SPDE approaches. You always get an isotropic field out. You don't need oversampling, and it really works well in a parallel framework. It's computationally very effective, and you can extend it to other domains and to non-stationary Gaussian random fields. So the paper is on arXiv. I think I've run out of time. I had some slides on applying it, but I let the chairman say whether, I think we'll ask some questions. If anybody wants to see it in a, so we basically applied it in a multi-level Monte Carlo, where we where we're basically doing, where we're doing transport in an uncertain medium. So you need to sample with our DNA solver on an SPDE, then we need to solve a PDE for the for the flow field, and then we need to solve a time-dependent PDE for the transport. And there it really made a huge difference for efficiency. I have a few slides. If somebody wants to see later, I'll show them later.
Thank you very much. Are there questions? Yes.
No, when you have too little padding, you can have negative eigenvalues. So that's when it fails in some sense. With sufficient padding, it always works, but then it might get extremely expensive, or your memory might not be sufficient. Yes. So all of these issues play a role, and they do not play a role in our case, because we start essentially our method produces the covariance with a periodized covariance function, and because the function is periodized, the FFT will work and will not produce negative eigenvalues. We didn't, certainly for the problem sizes we looked at, no. Ah, sorry. Yeah, that's what this is. Sorry, I didn't talk about that. That's this. Sorry, I show it here. So this is the stagnation comes here at the end. So eventually, so this line at the bottom is where the periodization error comes in. That's right. Yeah, the purple is no oversampling, but it doesn't converge. So, I mean, it doesn't, so it could, yeah, it stagnates. Basically, it's, yeah. The periodization error is so dominant that you can't see the H error. Yeah.
Yes, please.
Yeah, we need to look. Yeah, no, we haven't. But there's plenty of things that I've thought of where we could extend this to. I mean, not this last one. Oh, sorry. Where I'm most interested in is to go in this direction because I would like. Yeah, exactly. Mm. Yeah.
Are there other questions? So if not, let's thank the speaker again. So before leaving, we have a couple of announcements from the organizers. So the first one is that so on May 20th, so we will have a photo. So everybody's invited in front of the building 16 at 8:45 a.m. The second announcement for invited people. So there is a departure from Al-Quzama to Al-Balad on the same day, so May 20th at 4. So we shall meet at the hotel at 4 p.m. And there is so excursion in Al-Balad, and then around we go back to Kaust at 10:30 p.m. So, also we will enjoy a dinner at Andalusia there.